thank you to the organization of EPIC for this meeting and for inviting me. So I will talk about a contract that we had with the Spanish government. In fact, it's called CPP. It's a Compra Pública Precomercial, pre-commercial procurement, public procurement. So it was a call from the government on technological solutions for predictive maintenance of bridges and viaducts. I need to show you all these logos of the government and European Union because it's funded by those agencies. So the final client was ADIF. ADIF is the owner of the Spanish railways, and we set up a consortium with these 4 organizations. So T-Wave, Universidad Politécnica de Madrid, Ines Ingenieros, and ourselves. And this was a project which is already close to an end. We are exploiting the data, and so I will show what we did. So first of all, our core technology is the first, to our knowledge, is the first instrument that combines a laser Doppler vibrometer with LIDAR and with a multi-beam laser. So instead of having just one laser that goes in and scans the surface to reconstruct the modal analysis, we have an array of 65 or 128 aligned lasers, and by tilting the head, the sensor head, we get the full field of view in a very fast and simple way. So we have super dense data sets, and that allows us for some applications which are interesting. Okay, so the core of our instrument is this chip that you're seeing here. It's instead of having just one interferometer in the sensor head, we have 65 or 128 interferometers in this photonic chip, which is 1 centimeter from side to side. And this is our core knowledge, and is the ground to a couple of international patents. And this makes the instrument very robust, very insensitive to temperature changes, to harsh environment, very compact and easy to use. So we can measure from the phase shift between the laser that we emit and the light that is reflected on the surface. We can extract 2 important pieces of information. One is the distance, the absolute distance, and the other one is the frequency, the vibration frequency, based on the velocity. So when does this instrument become more interesting? Mainly when there's the object that we're measuring is difficult to access, because you don't have any elevation means, or you don't want to use elevation means, because it's small and you don't want to add mass, because it's clean and you don't want to contaminate it, or it's contaminated and you don't want to touch it. When it's cold or hot, you don't want to stick anything. When it's at high voltage, same thing. When it's a critical piece of equipment and you don't want to stop it to install strain gauges or accelerometers. When you need so many measuring points that it becomes impractical to use contact sensors. Or, for example, when you are studying living organisms or pieces of art that you cannot touch. Okay, so this instrument has applications in many kinds of fields. For example, here we see in aerospace structures. We see here this is a deflection, a torsional vibration mode of a wing of an airplane. You can use it for detection of defects in composites. You can use it for study of vibration and shock of electronics in under harsh environment, for structural health monitoring, of course, for car, automotive industry, NVH applications, high voltage, where you don't want to touch, biomechanics, and arts and heritage. So this project about SHM in viaducts. So this was a project funded by ADIF, so the owner of the Spanish high-speed railways, not the trains, just the railways. And what we proposed was to install 4 of our sensor heads in the pillars of a viaduct, which is in Córdoba, and looking towards the lower part of the deck. Okay. So the consortium that we built was taking care of different things. We took care of the sensor head. Destia took care of the communications of the data to a server, and also of the Ines Ingenieros. They took in charge the powering electronics. So we placed an optical trigger 1 kilometer before and 1 kilometer after the train passes, so that we can save power. And then we had also the Universidad Politécnica de Madrid, who was in charge of the modeling. So these are the sensors hanging on the pillars of the bridge and looking towards the deck. We painted the lower parts of the deck with a strip of road paint, which has these glass beads to increase reflectivity of the laser, mainly in the last points, because the angle was so small. First of all, we protected it from birds, which is something important. Okay. And then we started collecting data, and we saw some things which are coherent. Is that when you measure the trains passing at the same hour of the day, you get the same data because the trains are configured in the same way. And when you measure in the same day trains at different hours, you get different spectra because the trains are configured in different ways. So different number of wagons, different number of, the locomotives are placed in different places. And then we compared with accelerometers, because the viaduct was also instrumented with accelerometers. Here you see in purple, you see our data, and in black you see the accelerometers. And what you can see is that the data are quite, the fit between both is quite good, except for this first one. And that was because we went afterwards and we saw that the accelerometer was not correctly stuck. Also, we calculated and we measured the deflection in real time of the central point of the deck of one of the decks when the train passes. So since it's a hyperstatic bridge, we see this kind of behavior. So before the train passes, the deck moves up, and then it moves down, and then it moves up again, and then down again. So the Universidad Autónoma Politécnica de Madrid, they calculated this behavior, and we measured it, and we got very similar results. Even we get this kind of noise, which is not really noise. It's really high frequency vibrations due to the shock induced by the train on the viaduct when it enters. So some other projects that we are working on, this, for example, for the City Hall of Amsterdam. They want to know if the quays are being damaged. The quay is not really like a river; it's more like an open duct. Okay, so the walls of the deck of the quays could collapse, could leak and start collapsing or moving or wherever. So they have a service of people who are inspecting this day by day. And what we propose is to install our instruments on top of a car and increase a lot the productivity of this kind of inspection by measuring the frequency spectra of the walls of the quays. And many more applications that we can think of. For example, some 2 weeks ago, there was a piece of information in the news in Spain that says that 1/3 of the dams in Spain could be damaged and require technologists to monitor them in real time. Also, arts and heritage, also gas ducts and power plants. So these are many open possibilities that exist. So thank you very much, and I think this is all from my side.